How's it going? You guys have a good weekend? We all know now that section quiz 3 is posted. It's due before class Wednesday. Raise your hand if you're done with it already. Good. You feel all right about how it went? Good. Good. You can. I strongly recommend that you do not completely forget about categorical logic for now, because there's going to be an exam at the end of the semester, and I'll ask you some stuff about it again. But we're moving on to something new today. If you haven't taken it yet, please do make sure that you take it before Wednesday. Make sure that you give yourself plenty of time to take it. You only get one shot. It's not timed. You're allowed to have your notes and everything, and your book and everything. Just make sure that you do it by yourself. Otherwise, you're cheating. And you wouldn't cheat because you're not a cheater. I don't know if that argument really works, but it seems compelling enough for now. What we're starting with today is another approach to logic. We're still hanging out in deduction. So if your big gripe lately has been all of this is very abstract, very formal, feels a bit like math. Does this sound familiar? Like what we're doing feels a bit like math? It's gonna be even more abstract, more formal, more like math from here on out. This is what we're doing today. It's not as old a form of logic as categorical logic is. It would be hard to be as old or older than categorical logic since it goes all the way back to Aristotle. But it's a way more, I think it's a nimbler, it's a more far-reaching approach to logic. This is the style of logic that logicians today tend to use. And as Josh was pointing out, computer scientists as well. Which maybe shouldn't be surprising, because what we're trying to do with language is we're trying to formalize it. We're trying to make it as precise as possible. Precise enough that I could talk to a computer with language. This is still deduction. We're hanging out in the realm of deduction, where we're concerned with validity. And as we're all aware, hopefully keenly aware by now, validity is only about the abstract form of our arguments. It's not necessarily about the content. It's about if the premises are true, would the conclusions have to be true? So just like we saw with categorical logic, we're going to start kind of slow with propositional logic. We're going to make sure that everybody understands the vocabulary, everybody understands how all the parts move. Then we're going to learn some strategies for using these tools to determine whether or not arguments are valid or invalid. We're going to look at two strategies. Similar to like how we went through the categorical logic unit, right? We learned the basic vocabulary. We learned our A, E, I, and O statements. And we all saw just like how bad of a poop storm this could turn into if you were not sharp on your A, E, I, and O. Like if we got to the end and you were still not sure how to distinguish between A, E, I, and O statements, you were lost. Same sort of thing is going to happen today. So don't get lulled to sleep by how simple and straightforward this might seem, because these are the building blocks that we're then going to do more exotic things with in the coming class sessions. Okay, so propositional logic. So called because it deals with propositions. But then again, categorical logic dealt with propositions too. It dealt with categorical propositions. Propositional logic is about doing logic with multiple propositions put into relationship with one another. And I know you might be thinking to yourself like, categorical logic did the same thing too. But maybe I can make my point a little clearer by drawing our attention to some symbols, some new operators, some new concepts that we haven't seen before, that we didn't see in categorical logic, and that are going to be absolutely crucial in talking about propositional logic. We have here 4 logical operators, and these logical operators articulate some sort of relationship, or some sort of operation is probably the right word. Like, let's not mince it. We call them operators. They perform some sort of operation, just like a mathematical symbol performs an operation, just like the addition symbol, or the division symbol, or the radical, like, operates on something that we'll put in a function, right? These work the same way. Our 4 logical operators are conjunction, disjunction, negation, and the conditional sorts of statements, or the conditional operator, and they work a little something like this. Bob ran, Alice walked. Note something about this. Bob ran, independent, freestanding proposition all on its own, right? Bob ran is a statement. How do I know it's a statement? How do I know Bob ran is a statement? It's a complete thought, and it has a independent clause, has a verb, Keep coming. Because I could have a verb, right? I could say like, are you going to the dance? That's got a verb, going, right? It's a complete thought. Is it a proposition? It's a question. Why isn't a question a proposition? This is old stuff. Old stuff. Why isn't it? Yeah, Alman. It's a good start. Truth value. Yeah, that's correct. Has a truth value, right? So, are you going to the dance? You can answer yes or no, but you can't say true or false to a question. Bob ran, on the other hand, complete freestanding proposition. Bob ran is the sort of thing that can be true or false. What would make it true? Yeah, well, that's how you know it's true. But what would make it true is if Bob ran, then Bob ran is true. If Bob didn't ran, then Bob ran is false. Same with Alice walked. Freestanding proposition all on its own. Compare that, by the way, to something like all dogs are mammals. All SRP. In all dogs are mammals, if I was to represent that as all SRP, what is S in that? It's my subject, it's the subject. What is the subject of all dogs are mammals? Dogs. Is dogs a proposition? No. Dogs is a category. So here's the first thing that you need to be aware of and make sure that you don't get sucked into. For the last, I don't know how many class meetings, maybe about something approximately 2 weeks, we've been dealing with symbols, like letters as symbols for categories. If I was going to say something like all SRP, S represents a subject category, P represents a predicate category. But categories all by themselves, cats, dogs, mammals, those sorts of things, are not complete statements. They're not propositions. On the other hand, Bob ran, complete proposition. Alice walked, complete proposition. Bob ran and Alice walked, another more complex proposition that's made out of two propositions linked together with a logical operator. Represented this way symbolically, P and Q. P with this ampersand symbol, and Q. And that ampersand just represents the conjunction operator, that Bob ran and Alice walked. Do we see the difference between for example, how letters are being used in categorical logic, where the letters represented categories, and now our letters are representing whole propositions? This is one of the things that makes propositional logic very different than categorical logic. If you wanted to try to remember it, the letters represent categories in categorical logic. The letters represent propositions in propositional logic. Makes sense, right? Pretty straightforward? So simple, it's almost stupid? Good. Stick with me. We also have this logical operator, the OR logical operator, sometimes called a disjunction. Notice the AND was called a conjunction, the OR is called a disjunction. The symbol that we use for it is this little wedge. We use all kinds of different symbols depending on the convention. Sometimes that ampersand is a big dot. Sometimes the wedge is like a horseshoe with the curvy end pointed down. Sometimes the ampersand is a horseshoe with the curvy end pointed up. But we're going to be sticking to this symbolic notation. Know that there are others. For a conjunction, I have what are known as two conjuncts brought together with the conjunction operator. My two conjuncts in this case are P and Q is the whole conjunction. My two disjuncts in a disjunction are the two parts that are brought together by this OR operator. So I have P, that's one of my disjuncts. Q, that's another one of my disjuncts. P or Q is the whole disjunction. Good so far? And this is new stuff, right? We couldn't do and or in categorical logic. We're kind of learning new tools that are going to be useful when we're looking at natural language statements. Here's another operator, another logical operator. This one's called negation. The symbol that we use is this little tilde. There are other symbols that are used, sometimes a hyphen with a little ledge on it. And all that negation does is say not some other proposition, right? Or it's false that some other proposition. In this case we have, it's not the case that Tim studies. Tim studies is a freestanding statement all on its own. It has a truth value, could be true, could be false. It's not the case that Tim studies is a more complex sort of proposition. That takes the first one and says, yeah, whatever that one says, it's false. Notice this about the negation operator. It operates on exactly one thing that's immediately to its right. This is part of the syntax of how to use these symbols. This little tilde that says not, it's saying not to whatever immediately follows it. and it's operating on just one thing. That's different than conjunction and disjunction, which are bringing two things together, two conjuncts or two disjuncts together in a bigger, more complex statement. So notice the AND operator always has a conjunct to its left and a conjunct to its right. The OR operator always has a disjunct to its left, a disjunct to its right. But the tilde only needs something on its right. It doesn't join two things together. It only operates on one thing. Yes, Allison?
Translate it into Tim didn't study?
You could translate it into Tim didn't study, and we're going to get some opportunity to do something like that on the worksheet today. Yep. Any other questions about negation? Okay. Last but not least, and this is the kind of the burliest operator that we're going to look at. It's the one that maybe requires the most, I don't know, cognitive labor to wrap your head around. But we've seen it already when we were looking at some early comments about deduction. When we were looking at modus ponens and modus tollens, we saw that there was this if-then sort of way of linking up two propositions. So I could have a proposition P, Tim studies. Another proposition Q, Tim aces his logic exam. And then I can have this more complicated relationship between these two statements that I articulate with, if Tim studies, then he will ace his logic exam. And the symbol that I use to represent that relationship is the arrow, sometimes a horseshoe with the curvy end pointed that way, like an arrow. And notice it also, just like conjunction and disjunction, always links two things together. Do you remember what these two things are called? The two parts of an and statement are called the conjuncts. The two parts of an or statement are called the disjuncts. What are the two parts of an if-then statement? This is like before spring break. How well does your memory work? Folks at home, do you know? Folks in the studio audience? What's the part that comes before the arrow? Yeah, Amin. Antecedent. You got it. Antecedent. And maybe that'll kind of like jumpstart somebody's brain. What's the part that comes after? The consequent. Yep. So we have an antecedent and a consequent. And those are the two things that are being brought together by any conditional operator. You always have to have an antecedent and a consequent. It won't make sense if I just say, out of the blue, if I write as a statement like P arrow and then nothing else. That's not a complete thought, right? If P, then what, right? For the same reason I can't say like P and or, and that's all. Or I can't say PQ and. That doesn't make any sense. For the same reason that like if I was in a math class and I wrote like 2, 5 plus, and like here's my mathematical statement, my professor would say something like, nah, you're not using language right. You can do this with words as well. I can just make up nonsense statements, right? Hot to the leaf plant. Pizza. Happy? Question mark. That's nonsense, right? You have to use these symbols in a certain sort of order with a certain sort of syntax in order for them to make sense. Are we cool on these four operators and how they work? Let's dig a little bit deeper. Because one way of what we might say is defining these operators, talking about exactly what they mean, is to show how they change the truth values of the propositions that that they're operating on, right? So, for example, negation, which is the simplest of these operators because it only works on one thing. Negation, all it does is flip the truth value of whatever it's negating. So, for example, if I started out with a statement P, and that statement was true, then not P, or tilde P, is going to be false. If I start out with a statement P and that statement was false, then not P, or tilde P, is going to be true. Yeah, you got it. And I represent this on this truth table here that shows that, like, here are my two possibilities for P. P could be true, or it could be false. If P is true, then not P is false. If P is false, then not P is true. And this represents, like, any number of possible natural language statements that are representing the same content. So, for example, I can say, she's not French, which is to say, let's take a statement like she is French. Maybe I'll represent that with an F. F means she's French. Tilde F means she's not French. That was the question earlier too, right? Like, can you do this? Yeah. It's not the case that Pluto is a planet. Let P be Pluto is a planet. Then tilde P is it's not the case that Pluto is a planet. If Pluto is a planet, then it's not the case that Pluto is a planet is false. If it's false that Pluto is a planet, then it's not the case that Pluto is a planet is true. It's false that tomorrow is Sunday. Tilde S for where S represents tomorrow is Sunday. Makes sense, right? Pretty straightforward? That's for not. That's the simplest one. Gets a little more complicated, though. With conjunction, we'll notice right off the bat, this truth table that defines it up here is a little more complicated than before. The last one was pretty simple, straightforward. Just 2 rows, 2 columns. This one's got 3 columns and 4 rows. Why? Why so complicated? What's that? Yeah. I need a truth value for what? For each of the statements, and I have more statements in this too, right? So back on when I was looking at negation, there's just one thing, one statement that's being operated on by the tilde. Here we'll notice that with conjunction, when I say P and Q, I have to worry about the truth value of P as a freestanding statement, and I have to worry about the truth value of Q. And P could be true or false. Q could be true or false, and there can be any number of combinations, not just any number. There's exactly 4 combinations of these 2 truth values for these 2 statements. So they could both be true. P could be true and Q could be false. P could be false while Q is true, or they could both be false. And these are all the possible conditions that I could consider for P and Q. And I have some definition of what P and Q is going to be for each of those scenarios, for each of those possible conditions. When P and Q are both true, P and Q is true. That almost sounded completely redundant. But that makes sense though, right? If I say, I'm going to eat an apple and an orange, then in order for that to be true, what do I got to eat? Not just an apple? I can't eat an apple and say like, yeah, halfway there, let's round up. No, I have to do them both in order for it to be true. If either one of my 2 conjuncts isn't true, the whole conjunction is false. This makes it kind of easy to remember the conditions under which a conjunction is true because there's only one of them. It's only true when both of the conjuncts are true. Every other time it's false. And again, I can represent this in a wide variety of ways in natural language, where another way of saying this is I can translate a wide variety of natural language statements into this symbolic form. So for example, I have examples like here, Gene made a machine and Joe made it go. Gene made a machine, freestanding proposition. Joe made it go, freestanding proposition. Gene made a machine and Joe made it go. I can represent this way. And that's going to be true as long as both Gene did make a machine and Joe did make it go. If either one of those 2 things doesn't happen, the and statement falls apart and it's false. How are we doing so far? Am I like beating the minutia? Are you like, I get it, faster, faster? Okay, all right. Disjunction. Similar to conjunction. Also going to be 3 columns, 4 rows on account of disjunction also is relating 2 things together, right? So I have both P and Q to worry about. They could both be true. P could be true while Q is false. P could be false while Q is true, or they could both be false. And notice what's going on here with or, with this or operator. What makes it true? Yeah, as long as at least one of the disjuncts is true. This is what or means, or at least an inclusive sense of or means that at least one of my 2 disjuncts is true. I'm going to eat an apple or an orange. This inclusive or says, maybe I eat both, maybe I eat just the apple, maybe I eat just the orange, but I'll tell you what's going to make I eat an apple or an orange false is if I don't eat either one. That's the only scenario under which an or statement or a disjunction is going to be false, when both of the disjuncts are false. And yet again, and you'll see this in your reading and to some extent in your homework, and to some extent on the worksheet, wide variety of natural language statements that can be translated into this symbolic notation. You can have home fries or you can have grits. Unless you're going to have, here's an exotic version of it, unless you're going to have some home fries, you should just leave. Which is kind of like a fancy way of making an or statement. Have some home fries or leave. Disjunction good so far? Remind me. When is a conjunction true? When both the conjuncts are true? When is a disjunction true? When at least one of the disjuncts is true. When is a negation true? Yeah, but statements that are negations can be true. What would make a negation true? If the statement that's being negated is false, then the negation is true. Yep. A disjunction, true as long as at least one of the disjuncts is true. Conjunction, true when both of the conjuncts are true. And then here's our nasty guy, the conditional statement. The conditional statement is my if-then statement. Represents all kinds of possible natural language statements, natural language formulations. And we'll notice that we have a same level of complexity in our truth table that defines what the conditional is, because again, I have an antecedent and a consequent that are being linked together with this logical operator. P could be true, Q could be true, P could be true while Q is false, P could be false while Q is true, or they could both be false. And the only time that my conditional statement is false is when my antecedent is true and my consequent is false. Every other time it's true. This is a difficult thing for some folks to wrap their heads around, and we can talk more about this in the upcoming sessions. I'll say a little bit about it right now. If I have a conditional statement, if I have a statement like, if it rains, then I'll bring my umbrella, I'm talking about what's going to happen if it rains, right? Am I talking about what's going to happen if it doesn't rain? So if I say, if it rains, then I'll bring my umbrella, and it doesn't rain, and I bring my umbrella, you can't be like, busted. You said if it rains, you'll bring your umbrella, and it didn't rain, but you still brought your umbrella. I'll say something like, I only was talking about what happens if it rains. If it rains, then I will bring my umbrella. I didn't say boo about what happens if it doesn't rain. So if it doesn't rain and I bring my umbrella, I've not contradicted my if-then statement. If it doesn't rain and I don't bring my umbrella, I haven't contradicted my if-then statement. If it rains and I bring my umbrella, well, that's exactly what I said was going to happen. Definitely doesn't contradict my if-then statement. But if it rains and I don't bring my umbrella, then everybody has full license to call bullshit on me when I said before that, if it rains, then I'll bring my umbrella, right? It did rain. I didn't bring my umbrella. That's the only thing that's going to make this statement false. Does that make sense? And the ways that I can express this content in natural language can be very wild in their variation, and sometimes very confusing. We'll spend a little bit of time practicing with really complicated natural language translations, but not today. Today I want to make sure that we get the basics. So the really straightforward version of this would be something like, if it fits, then I sits. F is it fits. S is I sits. F arrow S is if it fits, then I sits. I sits if it fits, same content. I've rearranged some of the words, but it means exactly the same thing. Does that clear your BS tester? Is that yeah, that seems right. It sits if I fits is exactly the same thing as if it fits, then I sits. What about it fits only if I sits? Because I'm going to propose here that this means exactly the same thing as the other two. And this is a little bit weirder and complicated, more complicated, because we'll notice that the if went with fits here, if went with fits, now if is going with sits, but it's only if. Only if is different than if. Beware of this. You'll see this in your reading, and you'll see this on some homeworks that are upcoming. It fits provided that I sits. Same deal. Or here, yeah, the old Dos Equis formulation. I don't always fits, but when I do, I sits. Means exactly the same thing. All of them can be represented as F for I fits, or it fits, S for I sits, and F arrow S means all of these. How are we feeling? That last bit was a bit of kind of blah! But no, I want us to have a relatively simple and straightforward approach to this, at least for today. So we're going to get started on this worksheet here. I'll butterfly around and help you out with it. Notice that there are, well, first of all, notice that there are two sides. Everybody's aware that there are two sides to the worksheet, right? One of these sides is incredibly valuable because it has what each of those operators, what the symbols mean, and it has the truth table for each of those logical operators. That's going to come in handy. First 10 on the first part of this worksheet, on the other side from your little cheat sheet there, is a whole bunch of natural language statements that I would like you to symbolically formalize by taking all of the simple propositions, that is, all of the things that are the simplest versions of freestanding statements that you can find, represent those with a letter, and then represent the complex proposition by using logical operators with those letters. Does that make sense? So for example, let's look at our first one. Florida does not have snow. this looks like maybe it's a simple proposition all on its own. Let's make it just a little more complex. How about Florida does have snow? And it seems like what I'm saying here is it's not the case that Florida has snow. So how would I, what letter do you want to use for Florida has snow? F? F is a good one. S would also seem like it would make sense. But yeah, you can use anything that you like. So F is Florida has snow. Florida does not have snow would be? Tilde F. You got it. So that's the first part. Let's go through 1 through 5 on these, and then we'll check in. And then I want you to, once you finish 1 through 5, I'd like you to start working on the second part of the worksheet, which is way more complicated. On this second part of the worksheet, what I have is some formal statement, some well-formed formula. Something like this, P wedge Z, or P or Z, P with the or operator and then Z. A disjunction of P and Z. I've arbitrarily assigned truth values for all of these letters. P, Q, and R are always going to be true in this. X, Y, and Z are always going to be false. Given that information, I want you to tell me if each of these, the whole statement, is true or false. So let's look at number 1 just real quick. P or Z, or P wedge Z. P is true, Z is false. If P is true and Z is false, what is P or Z? Is it true or false? True? How do you know? What's that? Yeah, because the rule for the or operator, right? The rule for the disjunction is at least one of my 2 disjuncts needs to be true, and one of them is. P is true. So as long as at least one of them is true, then the whole thing is going to be true. What about R and X, where R is true and X is false? R and X would be false because the rule there is it's only true if both of the conjuncts is true. All right, good. Like I said, I'll be butterflying around. If you have questions, feel free to ask me. Feel free to work with your neighbors, and we'll put some stuff on the board with whatever time we have left over.